All right, so now we've really talked about electrophilic aromatic substitution in great detail. Electrophilic aromatic substitution. Now it turns out that we have a way of making EAS faster, and that's by putting an activating group on it. Okay, so substituted benzenes may undergo EAS reactions with faster rates than unsubstituted. And that, the key word here is may, right? What is rate? What is meant by the term rate? Okay, and what does that mean in terms of our energies? What is rate? So toluene undergoes nitration. Here's toluene down here. Remember this? Undergoes nitration 25 times faster than benzene. Wow. Okay, that means it's a lot faster, right? So why is the reason? It's because the methyl group activates the ring through induction. Important word here, induction. Matter of fact, circle it. Write it out. Say it out loud. It activates the ring through induction. Explain how. All right, so what's this going to give us? What product is this going to give us? Well, if we were just sort of memorizing what we had before, we were taking benzene rings and we were always putting a substituent right here. Right? Okay. But that was when there was no when there were no other substituents on here, right? So is it going to go here? Well, again, of course, it was just randomly that we're putting it there just for note-taking's sake, right? So it might go there, it could go here, and you can see that these positions are not the same now, right? Ortho, para, meta, meta, ortho, right? So these are the three possibilities. Let's look at this. Substituted benzenes generally undergo EAS reactions selectively, that is, regioselectively, or where things go, okay? So nitration, for example, of toluene is going to go 63% ortho, 3% meta, which is basically none, and 34% para here. Okay, so it looks like it predominantly goes in the ortho position, right? All right. Why? Well, the relative position of the methyl group in the approaching electrophile affect the stability of the complex. And let's look at how, at the sigma complex, and let's look at how. Suppose, and if you were just given plenty of time, which of course, you know, in theory you have plenty of time, right? If you were given plenty of time and a piece of paper, you could go through and make predictions yourself, just based upon shape and polarity. All right, so let's consider each position first. I'm going to do sort of what you might have been able to do without a book or without a professor, right? Just to consider it. Ask the question, what's it mean? So look at this. Let's go here. Let's say that this is, you know how to make this electrophile, right? That was in video, I think 19.4, I think. Okay. So you make this electrophile with sulfuric acid, and then let's suppose that these electrons come and make a bond, right? If that happens, look what happens here. You draw your what is this? Oh, resonance hybrid, right? And the resonance hybrid is going to look something like this. A methyl group. Right, remember that? A little bit ugly. Okay, remember that? Well, now what's going on here? And this is a CH3, right? It's a methyl group. Okay, so what's going on here? What can we see? Well, if alkyl groups are electron donating, and you've got a plus charge here in one of your resonance contributors, right? That's good. You've got an alkyl group. This is now a tertiary carbocation. Right? So if the ring attacks from the ortho position, the first resonance contributor of the sigma complex is stabilized. How so? I just said it. Say it again. You say it. Is the transition state also affected? Look at that. Is the transition state also affected? Okay, so now consider the meta attack. So if the bond goes here to the meta position, the new bond to the nitro group goes to the meta position, well then you're going to have a plus here, a plus here, and a plus here, right? But never a plus on the carbon that has the electron donor, right? There's my electron donor. You see it? And this carbon never has the plus charge on it. Okay? So this is not helpful. It's not bad, right? It's just not helpful. Okay? So this one, though, if it goes to the para position, then we get, what's this? Carbocation. Another resonance contributor has got the carbocation where the electron donor is, right? And then here's the 3 carbocations, right? So this is stabilized. Through what process? Say it out loud. This is stabilized through, say it out loud, induction. Okay, induction stabilizes that, hyperconjugation. All right, so if you have an alkyl group on a, let me take a second to look where I am in the, okay. So if you have an alkyl group on a benzene ring, it's gonna activate this because it's bringing electrons in and it's stabilizing the carbocation intermediate, the sigma complex. All right, now, explain this trend below. So the ortho product predominates. Why does the ortho product predominate? There is some crowding here at this position, right? But the ortho product predominates. Why? For statistical reasons. What statistical reason? Well, I'll tell you. There are 2 ortho positions for every 1 para position, right? So I'm going to go back a few slides now. Let me go back to the first slide. There are 2 ortho positions for every 1 para position. And ortho was 63% and para was 34%, right? Well, if there's 2 orthos for every 1 para, this ought to be double. Ortho ought to be double. Is it double para? Is it double? No, it's not. Double would be 68%, right? So it turns out that the steric crowding, I'm going to go back to the slide where I was then. The steric crowding, steric hindrance causes ortho to be slightly less than double, even though it's got double the possibilities. Okay, can you see that there's only 1 para possibility? But it could go either ortho, right? All right, so if there was no steric crowding, you would expect it to be exactly double. All right, or no other kind of overlap or hyperconjugation or whatever. Okay, so explain this trend below. Do you know why that this is the meta attack is so high in energy? Where would benzene be? You should show, overlay the energy diagram for benzene. Which would it look like? Which of those 3 would it look like? All right, so let's move on. The methoxy group now also activates, but even much, much more, for 40 times what the other one was. Wait, 4? Is that right? I don't know. A lot more what toluene is, but 400 times that of benzene. 400 times. Benzene does it through induction. Toluene does it through induction, right? Because alkyl groups are electron donators. I'm going to do this. I'm going to write this. You've got to see this in your head. In case you're falling asleep, I'm going to write this out. And you write it out too. Alkyl groups are electron donating. Alkyl groups are electron donating, okay? This is not an alkyl group. That's an alkoxy, right? Specifically, it's methoxy. Okay, let's go back to red. So, through induction, a methoxy group, is that withdrawing or donating? It's withdrawing, right? Through induction, it's withdrawing because oxygen's electronegative, right? You would expect it to be polar like that, and it is, okay? However, the methoxy group donates, through resonance. Okay, so we've got these two methods now. I'm going to do them, and I'm going to highlight them. I'm going to try. I haven't done this for you yet, I don't think. Highlight. Induction. Resonance. I should use the highlighter more. That's pretty, isn't it? Induction and resonance. Those are our two ways, okay? Now, methoxy is going to be withdrawing through induction, but donating through resonance. Why? Why? Because of this right here. Do you see this? So these electrons can be fed into the system, right? Look at that. And there they are. Okay? So through resonance, right? This is one big resonance structure. How many resonance structures do you see here? How many resonance structures do you see above? 4. 4, 4, 4. There are 4 resonance structures. Why? Okay, look at that. Why am I even bothering you with this? Well, because it's important to be able to count. And when you're counting this stuff, that sounded very condescending, didn't it? I'm not going to even splice it out. No, it's important to be able to account for electrons. Right, you've got to be able to figure to be able to see where things are, and when you do that, questions which would otherwise be very difficult become very plain. All right, so this one is the same as this one, right? So I should have just drawn it like a circle. So there's really only 4 resonance structures here, and it'd be so good if you could draw. Well, no, not so good. You must draw the resonance hybrid. My handwriting was so nice this morning, wasn't it? Draw the resonance hybrid for this. Okay, and then tell which resonance structure contributes most to the resonance hybrid. All right. Okay, so the methoxy group activates the ring so strongly that polysubstitution is difficult to avoid. So if you put bromine in here, if you get enough bromine, where am I here? Enough bromine, it's going to tribrominate that. 100%. Wow. Okay, now activators are generally orthoparadirectors. Orthoparadirectors. And you can see why. Via induction, or resonance. Via induction or resonance, electrons get fed into the system and stabilize the intermediate. Okay. Now, look at how anisole, or the methoxy group, stabilizes this intermediate. So if you get ortho attack, if you get attack at the ortho position, right, a new bond is here. There's the new bond, which is being implied by that, right? There's the new bond right there. Then you have a carbocation here. The carbocation through resonance goes around the ring, not all the way around, right? Just to those 3 positions. But when you get to this position, you have an additional resonance contributor. Look at that. This is the additional one, and this is the magic one here. Probably the next page is going to say which one is the most important structure. I've seen this question show up in question banks, probably every question bank that is published for these. This question shows up because it's so important. This is the reason why. This is the reason why methoxy groups are OP directors. All right, it's this structure right here. Now you don't have that kind of stabilization here, not here. All right, in the meta position, but in the para you do, right? Remember this? There's the new bond right there. Okay. Now walk that carbocation around the ring. It's here, and then it's here, and then it's here. Which one is the important structure? This one. Right? Can you see it? That's the reason why that methoxy or alkoxies are orthopara directing. All right. Well, finally, we can look at our energy diagrams. Just what you would expect. Now, in this case, the para product is the major product. I don't think we're given percentages here. Oh, yeah, we are. Yeah. Look at that. We're given percentages. I'm going to go back a couple slides. Oh, I don't have it here. Sorry. Nope, I don't have it. In this case, but it's in the book, we're told that para is actually 67%. Ortho is 31%. Why is that? In a word, give an answer for that. Why is that? Okay, all activators are orthopara directors. All activators are orthopara directors. Give reactants necessary for the following conversion. Okay, so do this as a synthesis problem and see if you can also see why it's clever. Why is this? An intricate conversion. Okay, let me give you a hint. Whatever you do for step 1 and 2, see what happens when you switch them. Okay, see what happens when you switch them. All right, now go practice with conceptual checkpoint 19.12. Good luck.